Yeah, so it's great to have Idan as our speaker today. So Idan is an ideal postdoc in all senses, and he jointly hosted with UIC and TTIC. Idan works on really a lot of different aspects of foundations of machine learning. He's a winner of ICML Best Paper Award. I should look at my notes for exactly which one. And 2024, and selected as a Rising Star Data Science at UC San Diego, and just a bunch of great work on all sorts of aspects of learning theory and decision making. And so today, talking about variable expressions and distribution shift. Go for it.
Thank you, Avram. Yes, I will talk about two papers with Nati in the audience. Where the main theme is computational learning theory. The first paper would be a negative result, hardness result for learning regular expressions. And the second one would be more like a positive results. How can we circumvent negative results, computational negative results, by using a distribution shift. So the first paper on the hardness of learning regular expressions is with Lev. Nati, I put a picture of you with my daughter. I hope you're not mad. This is Nina. We just arrived to Chicago. This is Nina yesterday.
We'll should have her on the next paper. Or maybe she's typing it now. I don't know.
and Galvardi. Yeah, so that was at Nati's Sukkah. I highly recommended to go visit in Sukkot. Huge holiday. Okay, so learning regular languages is like one of the most fundamental questions, I guess, since the beginning of learning theory. So let's say you want to learn some regular language. Let's say strings that contain the substring 101. And let's say there is some unknown distribution over the strings, and there is a function that indicates whether this string belongs to this regular language or not. So I would collect labeled examples, the strings, and see the indicator function we're gonna label them. But we need to choose a representation for C. Because for now, C could be any function. So one known representation could be a DFA. The DFA, deterministic finite automata, will represent the language. A DFA for this language is going to look like that. Another common choice of representation would be regular expression. This is going to be the regular expression for this language. And actually, they characterize same languages. There are other options of representations, but these are common ones. And both of them make sense in different contexts. And Clean in 51 showed that this is indeed equivalent. Okay, so most papers are about automata learning, since even before like the definitions of PAC learning, Gold in 67 showed that regular languages you can learn them in the limit, only for positive examples. This became much more popular recently for language generation, this model. But there is no like finite sample guarantee, just as the final, like if you're going to see enough examples, then you will be able to identify the automata. Dana Anglin showed that if you allow membership queries in addition to random examples, actually you can learn efficiently DFA by a very famous algorithm called L-star. Pitt and Wormels showed that if you're using only random examples, that it's part learning hard to learn DFA in a proper way, meaning the algorithm must output DFA. And then a more general result was showed a year later by Cairns and Valiant, where they showed that it doesn't matter what the algorithm can output, any function that is evaluated in polynomial time, still it's PAC learning hard to learn DFAs, and they needed cryptographic assumptions, breaking some one-way functions. And there are like many papers about learning.
Naive question. Are you going to tell us something about the VC dimension of it?
Okay, good.
So
information theoretically, everything is going to be easy to learn in this context. The question would be only on the computational complexity.
So the VC dimension is finite, at least for
Yeah, so if you look at strings of length at most n, the VC dimension is going to be small, and sample complexity is not the problem. The problem is runtime of the algorithm.
The VC dimension doesn't scale with the number of states in the DFA or
Logarithmically,
logarithmically?
and then we're happy with that. Yeah, good question. Look,
It's gotta be linear in number of states. But anyway, but it's a function of number of states. So
yeah, it's a function. Yeah,
we're talking, so you're talking, running time and samples, polynomial index, description length of the
Yeah,
function.
exactly.
Yeah.
representation of the. Yeah, but the question is about the computational complexity. No, I'm not worried about the sample complexity. I guess it should be linear, which is fine because we want the polynomial dependence on the description length of the concept.
And log n, right? Not
And log n, yeah, if you
almost linear.
Yeah, actually we wrote it very explicitly. Yeah. But we're happy with that because it's polynomial in the description length of the DFA. Good. Okay, so it's very natural to ask whether we can learn regular expressions because this is like really very basic tool that people are using for a bunch of pattern matching tasks, text search, input validation, compilers are using that, search engines, implemented in almost any programming language. So it's not natural to ask whether we can automate this process. And simple, okay, let's try to go by the naive solution. Okay, I have a DFA. There is a equivalent regular expression. If I had an efficient algorithm for regular expressions, then I could learn the DFA. So it must be hard to learn regular expressions. But this approach doesn't work because this conversion from DFA to regular expression could be exponential. And then if I have an efficient algorithm that depends on the size of the regular expression, it doesn't mean that I have an efficient algorithm for solving DFAs. So the problem with the naive approach is that indeed regular expressions and DFAs are equivalent. We all learned that like in the first few lectures in computational models. But the conversion in both sides can explode exponentially, which most people I talked to didn't know this fact. Like they knew that there is one blow up in one side, they weren't sure about the other side. It was also new to me. So yeah, so we cannot conclude anything about the learnability, computational hardness of learnability of regular expressions from DFAs.
You mentioned DFAs is hard.
Yeah, DFAs are hard. Yeah. Yes, they are hard. Yeah, I will show also a table like summarizing everything. Okay. So the goal of this paper is we're going to show hardness of learning regular expressions. And we show that in some sense it's harder than learning DFAs because if I have membership queries, I can learn efficiently DFAs, but it's not going to be the case for regular expressions. So they're not equivalent in that sense. About the equivalence with non-deterministic finite automata, it's an open question. I don't know. Okay, so this is just like an overview of like what's the goal of this talk. Any questions? Is the problem clear and like why it's not solved by something trivial? Okay, and actually this was not his idea. I came to him asking like about cool research questions, and he was like, I'm teaching a class for 10 years about machine learning, and I thought it's like known, and he couldn't find any reference. So yeah, it's a really nice idea of like looking at the representation. Actually, like people did. I don't know why people didn't think about it, but okay. So, are you all familiar with regular expressions? so I will go quickly. There is an alphabet, sigma, just binary. Sigma to the n are strings of length n. Sigma star are strings of any length. There is the syntax of regular expressions over this alphabet. It's defined deductively. The base case is the empty set symbol, epsilon, the empty word, and any symbol from the alphabet. And then if I have two regular expressions, then if I take their union, it's also a regular expression. If I take the concatenation, it's also a regular expression. And if I take the clean star, it's also a regular expression. Then there is what it means actually. This is just string, so it represents a language. So for the best cases, L of the empty set just represent the empty sets. L of epsilon represent the set with the empty word, a word of length 0. L of a symbol just contains the language with the symbol. And then for the operations, it's just going to be what you would expect for union, for concatenation. And yeah. So for example, this is a regular expressions for the language that contains a substring 101. So 01 star could be epsilon, could be 01, could be 00, 01, 1011. Okay. Okay. Also finite automata, because we're talking about it, so let's define it quickly. It's just a tuple, contains the alphabet sigma, finite set of states q, initial state q0, transition function that reads a symbol in a state and moves to a specific state. A subset of q that is our final states, accepting states. And given a word, when we read this word walking through the automata, if we ended in an accepting state, then this word is in the language of the automata, and otherwise it's not. And non-deterministic automata, there are a few distinctions, but the most important one is that you can move to a few states when you're on a specific state and reading specific symbols. So this is a non-deterministic transition. Okay, so I think this is was already interesting when I started to study this problem. So red lines imply that there is an exponential blow-up in the conversion, and blue means polynomial blow-up. So when I translate regular expressions in DFAs, the blow-up is exponential. NFA to DFA, it's known that this is exponential. That's like a known construction. DFA obviously is just an NFA. And regular expression in NFA, it's asymmetric. If I take the NFA and convert it to regular expression, it's exponential blow-up, but otherwise it's polynomial. Okay, so just example of languages that realizes this that's the blow-up between DFAs and regular expressions. So let's say I have the language, the kth from last letter equals 0. So it's easy to write the regular expressions that is just linear in k. This is the regular expression. Read whatever strings you want, then read 0, and then read 3 specific symbols that are 0 or 1. A very natural language. But actually DFA must use 2 to the k states to count all of these suffixes, which the regular expression avoids. So formally, if you want to prove it, you need to use something called Maillet-Merod to show that all of these 2 to the k suffixes belong to different equivalence classes, and each equivalence classes represent a state. Very simple. I think this is like pretty known to most people. What I didn't know before I studied it is the opposite direction. It's not so easy to prove. So
just for that first thing, but for an NFA, you could just have, 0, 1 star just represents something can either stay itself or go to the next thing, looks for the 0, and then just k states after that, right? So I guess with an NFA, you can get rid of it.
you can do that, yeah, for sure.
You just have that.
Yes, yes. Correct. Good. Okay, so let's find the language, natural language, where the DFA is actually exponentially more compact than the regular expression. So the language is all strings such that the number of zeros are 0 modulo n, and the number of ones is 0 modulo n. So, okay, DFA could do it easily. Just states are going to be a tuple that counts the residue of each symbol. Then you need n squared states, and this is easy. So DFAs are really good in counting modulus because they can reuse the states. But actually, regular expression, it doesn't have memory, and it must unroll all combinations of residues. So it's intuitive. In order to prove it, there is some concept that was new to me called the star height of a language. And star height is how many nested clean stars operators are within your regular expression. And it's not easy to lower bound this guy, but once you know how to compute star height of regular expression, then you can show that the regular expression must grow with the size that it 2 to the star height.
What do you mean all combinations? I guess I wasn't sure what combinations you're referring to that explanation.
So here the DFA, remember
The mod.
remember the mode, but if you want to write a regular expression, you must just write everything. You cannot reuse the same expression. You just write down all possible strings. It's impossible to do it otherwise. If you try it, you will understand, but to prove it is not really not so simple. And yeah, so there are like two communities. There is one community that are studying this compactness of these objects. They are not doing learning usually, and like there are results from like the last few years also. And there is the learning community where I think intuitively people think, okay, regular expression is just like a DFA, and maybe, I don't know. And so yeah, we needed to read a bunch of papers from the other community to bridge the gap. But this is a really active research. Like there are many open questions there, and people are studying those compactness representations of regular languages. So yeah, these two languages are quite simple and useful probably. Okay, so if this is new to you, I'm already happy that you learned something. Okay, questions? Okay, so let's define quickly pack learning. There is a concept class C, which we parameterize by the length of the strings it reads. So it's a series of collections of functions Cn, which Cn are functions from strings of length n to 0, 1. And we say that the algorithm A pack learn C for any epsilon, delta, and n, for any target function C star, for any distribution dn over xn, the following holds. If we have an IAD examples where x drawn from dn, then the algorithm outputs a description of hypothesis H such that with high probability the error on random example is small compared to C star. And what is really important for this talk is that we care about tractable algorithms. So Cn is tractably learnable if A runs in polynomial time in n epsilon and delta, also in the size, the description of the target concept, but usually we assume this is already polynomial in n. So it's not really important. And another important thing is that the hypothesis the algorithm outputs should be evaluated efficiently. This is a key point. Maybe a circuit, but I need to be able to compute h of x efficiently. Okay, so that's what it means, efficient pack learning in this context. Yes.
So if it means say pack learned, I guess implicitly your number of samples is polynomial.
Yeah, so if the runtime is polynomial, Essentially the same. Yes. Good. So this is the minimal thing you can say. It means polynomial input. Thanks. Good. Okay, so there is also the model where we allow queries. So membership query oracle, for any x in the input space, just returns the value of c star of x. And in this model, in addition to random examples, the learner may adaptively query this membership oracle. And it has been shown, I think for the first time by Dan Angluin, that this matters. Like learning DFAs become efficiently learnable once you allow these queries. And learnability and tractability are defined similar. In the second part of the talk, we're going to talk about what it means to adaptively query or non-adaptively query this oracle. Okay, so this is the important slide. This is the current state of what we know about learning regular languages. So in bold is our result. So polynomial in n, the input size. DFAs is known that this is distribution free hard under, okay, so this is the cryptographic assumptions, RSA, factoring manual Blum integers, quadratic residues. These assumptions are like more recent. Random case set is average case complexity. Whether we can refute whether randomly KCNF is satisfiable or not, large enough KCNFs. Local pseudo-random generator is, we'll talk about it a little bit, is a vector random generator that is using only local structure, used a lot in cryptography recently, and sparse learning parity with noise. Yeah, we'll talk about it later. Okay, so it's known that learning DFAs in PAC and also under the uniform distribution is hard, but it's tractable if I allow membership queries. NFAs are hard everywhere, but we don't know if it's hard under the uniform distribution when we allow queries. Answer could go both ways. Yeah, I don't really know what should be the answer. And okay, regular expressions, when we use just vanilla ones with or concatenation and star, we show that it's in distribution-free PAC learning, it's hard under all of these assumptions. When we need to tailor it for the uniform distribution, we can do it only with the local PRG. It's really non-trivial to show this distribution-specific hardness in PAC. In fact, I know maybe 1 or 2 papers that are doing that. It's also hard, distribution fee hard if we allow queries. Again, under the uniform distribution, if we allow queries, it's an open question. Don't know the answer. And okay, if we allow more operations to the regular expressions, if they're even more succinct, for example, if I add intersection or complement in regular expressions, which are like operators that are really used in practice, then everything is hard. Even with queries, even under specific distributions. Any question about the type of results?
So to make sure I understand correctly, the uniform distribution is over the strings that we have.
Yeah, and sometimes it makes a difference. Sometimes you can learn. Yeah, I will talk about it later. There are some cases when you can learn efficiently under the uniform distribution. When you allow any distribution, then it becomes hard. Yeah, so this is a really interesting open question. I have some ideas how to tackle it, but it's not easy.
So what do you think is the answer? Is it hard or is it try?
Could go both ways. The problem is that I think maybe there is one paper that show distribution-specific hardness with queries. It's from '93 by Haritonov. This is the only paper that exists that shows distribution-specific hardness with queries. And for PAC, I think there is one recent one with local PRGs. Maybe there is another one, but there may be 2 or 3 papers that shows distribution-specific hardness. And the reason is that you need to find, on the one hand, you want to find an assumption that is well accepted, that this is hard. On the other end, you want the assumption would be flexible enough so you can show hardness with respect to a specific distribution. So it's really important to find the right assumption if you want to prove it. And they found it 4 years ago, this pseudo-random generator assumption. But yeah, there are not so many tools to show that. That's what I'm trying to say. So yeah, I don't know. I will try to find an algorithm and then see how it goes. More questions? So we'll just give you some flavor of how to prove these results. Some of the proofs are really easy. There's one complicated proof that I won't show you. So the first result is by reduction from DNFs. So what is a DNF? There are n Boolean variables. Literals are just a variable or negation. A term is a conjunction of literals. And then a DNF is just a disjunction of terms. The size of a term is the number of literals in it. So it's at most n, because it doesn't make sense to include the variable and its negation. And the size of the DNF is just the size, if I sum of the size of all terms. Okay. So yeah, until recently, it wasn't known that this is hard in PAC learning, which is maybe a bit surprising. So yeah, so the claim is that if I have a DNF over n variables with m over m as a function of n terms, then it's easy to construct a regular expression, equivalent one, where the size is the number of terms times the number of variables, such that they are equivalent. Any x that satisfies the DNF belongs to the language of the regular expression. So for any DNF, we can just construct an equivalent regular expression such that all variables, all assignments that satisfy the DNF are going to be rolled out by the regular expression. And the idea is simple. Okay, this is an example. So the first term, I have x1. I don't have x2. I have negation of x3, and I have x4. So because I have x1, I'm going to write in this object, I'm going to write 1. x2 doesn't show up, so it doesn't matter if I have 0 or 1. So if a variable doesn't show up, I'll just write 0 or 1. x3 shows up in negation, so I need to write 0. And x4 exists, so I need to write 1. So basically for each term, I'm going to construct a regular expression that takes care of any variable of the n variables. If it doesn't show up, I'm just going to write 0 or 1. And I will do it also for the second term. So basically, for each term, I'm going to have a regular expression of size n, O of n. And then I have m of n terms, so the size is going to be m of n times n. Very simple. Makes sense? Okay. Okay, so as far as I know, these are the known hardness results for DNFs. So Danieli and Schwartz, also another paper previously with Nati Lineal, showed that under average case complexity, it's hard. It's a nice breakthrough. 2021, Danieli and Vardy showed it under different assumption. And yeah, people from cryptography are working on that. For example, Appelboim, and they showed it under sparse learning parity with noise. But this is fairly new. Also, there is an old paper by Anglo and Haritonov that showed that queries shouldn't help for distribution-free pack, meaning if it's hard without queries, then it's going to be hard with queries under the existence of one-way functions. Okay, so this means that we can conclude that it's hard to learn regular expressions even if we have queries, and the regular expressions should be of polynomial size, actually for any polynomial size. So
Where the membership queries come in?
So if it's hard to learn DNFs with queries, then we constructed an equivalent regular expression.
Okay. Distribution free, got it.
Distribution free, and also, this is a really important point, because the reductions with queries are much more, your intuition is right, but take a look at the equivalence, where is it? Yeah. We construct a regular expression, this is equivalent to the DNF.
Good. So it's not changing the examples at all. It's not like repeating.
Right. If it would, then we should
Yeah,
be
yeah,
very
yeah.
careful. There is another requirement that should make it work with queries. For example, with DFAs, and DNFs, it's not going to work.
Right.
I think this is the example you have in mind. When I reduce DNFs,
Right, you blow up the examples there, but then the
Yes.
queries. Right. Good. So here it's the same example.
good point. Took me some time to convince Lev, for example, why it works in this case and not in the other case. So just to summarize what Avrim said, is to show those reduction with queries, you should be much more careful. Because when you modify the examples, maybe the membership oracle for the new problem can ask things that are not even in the input space of the original problem. Okay, let's speed up.
If I remember right, the intuition of the Anglo and Haritonov result is basically, because SAT is hard, and so it's hard to find positive examples for even a known satisfiability instance. Similarly, it's hard to find negative examples for a complement for a DNF, even if you know it. You sort of take the thing you're trying to learn and you and it with this thing that makes it impossible to ask a query where the answer isn't yes. It's like, and then what they need to show is that in addition to SAT being hard, even if you have like a distribution over positive examples, you still can't create new ones you've never seen before. And so, even if you have this button you can press that gives you, over some crazy distribution, you still can't create a query that in this case would say, what's the hard case for DNF? So they will say negative. Like anything you can think of would be positive, right?
Cool.
So, and that goes through. Okay, good.
This is the intuition between.
Yeah, that was a nice result.
So maybe I will speed up. Okay. What I want to say is that if I want to show it for the uniform distribution, then going through DNFs is not going to be very helpful. It's not known to be hard. There is a quasi-polynomial algorithm. It's a major open problem, whether you can do it in polynomial time or actually quasi-polynomial time is necessary. So instead, we work directly with an assumption, and we show that if you have a weak learner, if you have a learner for regular expressions under the uniform distribution, then I can break an assumption, cryptography assumption. So these proofs are much more involved. You're working from the wires, like you're not doing any reduction. You need to do the hard work. This is a complicated proof. But it's based on a beautiful method by Danieli and Vardi in 2021. I'll not show that. Yeah, I guess I will skip also this slide. If I add more operations to the regular expression, then I can reduce Boolean formulas to extended regular expressions. And Haritonov showed that learning Boolean formulas under the uniform distribution, and in fact under like any non-trivial distribution is hard. So you can. This is also a simple reduction. Yeah. Maybe. Yeah. Okay. Talk about that fast. There is a paper about learning a subclass of regular expressions called shuffle ideals. Well, what is a shuffle? There is an unknown string u, and u is a subsequence of a string. So this is a language that is the shuffle of u. And I talked to Arya and to Dana, and their goal was, not to show hardness, their goal was to find a simple subclass for a positive result. So indeed they showed that it is, you can efficiently learn it in back, this subclass for regular expressions. And also under some nice distributions in the follow-up paper. But they show distribution-free hardness of improper learning also of this subclass. The thing is that their alphabet is not binary, and they couldn't do it for binary alphabets. And the hardness doesn't follow when you have membership queries. So we can use their construction to show that general regular expressions are hard under cryptographic assumptions, which does not follow from the DNS. So it gives us something. I'm just saying that some people try, I think they didn't pay attention to the fact that regular expressions are not DFAs, but they tried to find a subclass that they could do something. And indeed, like for many interesting distributions, it's actually efficiently learnable. Yeah, I think this is the only two papers I'm aware of that actually learn regular expressions.
In fact, yeah, I think in that paper they kind of implicitly assume that it's known that
I guess.
that it's hard.
Yeah.
That regular expressions are hard.
And explicitly, I asked them
Yeah.
to see that I'm not missing anything, and they said that what you said is what we know. Like we didn't pay attention to this compactness issue. Okay, so takeaway is that, okay, you have a concept, you can represent it in a few ways. What matters is the description length of the concept, the complexity measure. And it's important when you want to understand when you can learn efficiently. And okay, open questions, learning under the uniform distribution with queries, and showing a separation or an equivalence between efficiency of learning regular expressions and NFAs. Okay, let me skip to the 20 minutes, 15. Okay, this is by this group of people: Marco, Elisabetta, Tio, Gal, Nati, and a new paper with ongoing paper with Nader Bashuti, and this is Nina in the Zoom 2 days ago. Okay, so what's the point of this paper? So there is a paradigm shift, I think, recently, that in the past, I think we used to fix the training set, maybe to clean it a little bit, fix the training set, and then try to improve the learning algorithms and the models. And lately, I think what we see is that we fix the architecture, we fix the algorithm, some variant of SGD, but then there are complicated methods of how to choose the data, how to choose mixture over data to improve LLM's performance. So that I would call a data-centric paradigm. And in this talk, we're going to show some version of data-centric AI, where if I can choose the training distribution differently, the target distribution is the same, then I can turn computationally hard problems to tractable ones. So I'm just choosing the training distribution. I'm not choosing, I'm showing that there exists a training distribution that makes the problem easier. Okay, okay, we talked about PAC. I just want to say that in this setup, it's important also to have random noise. So instead of just a realizable case where the y's are deterministically labeled by H star, there is also could be a noise, noisy distributions where with probability 1 minus the noise parameter eta, we're going to observe the right label, but with probability eta, actually the distribution is actually the opposite label. Okay? And the objective is, because the distribution is noisy, is to get error that is at most eta plus epsilon. Okay? It's important because some setup, the noise is really important for the hardness of the learning problem. Challenges are computational and statistical. This talk is about the computational aspect. Okay, so traditional distribution shift is usually negative. You train your autonomous, okay, this is generated by GPT, I think. This is a weird sign, I don't know, hallucination and signs. I just kept it. Okay, so you train your autonomous car in California, but actually you want to deploy it in New York. You have many samples, many time to train your car in California, but only a few examples from New York. Usually what this type of work says is that, okay, you're gonna pay something. What you're gonna pay is gonna depend on the distance between those two distributions. And it has various names: multitask learning, transfer learning, domain adaptation. Each type of model tackle different problem, but this is usually the main setup of this type of settings. So in this paper, we're gonna talk about positive distribution shift. So even when we care about specific distribution D, it's still better to find a different distribution D prime to train on. Okay? The benefit is going to be computational. There is a recent paper by Marco and co-authors that they show some statistical benefit also, this type of thing. Okay, general definition, not very accurate one, just in the spirit of this model. We say that the learning algorithm, a PDS, positive distribution shift, learns a distribution D, that is, D of X is the marginal, and it's labeled by H star. Could be also noise in the label. Using a different distribution D prime, where the sample size is M of epsilon, runtime is T of epsilon, such that we sample from D prime, but the error is with respect to D, to the target distribution. I'm hiding what this new distribution should depend on. Should it depend on target distribution and the target concept, or more realistically, just the concept class? So there are a few frameworks for that. Different from distribution-specific learning. Okay? Distribution-specific learning says, I'm going to make an assumption on the marginal distribution. It's Gaussian or very nice distribution. And then the algorithm is efficient with respect to this distribution. Here it's not the same. It's not the same thing. Here I want to say that for any target distribution, there exists some D prime that makes the problem easier. But I do care about any distribution D. I'm not making an assumption of D. So this is. Does it make sense? Okay. So the focus is on computationally hard problems in PAC that actually in this model are efficient. And there are three aspects to this type of results. First one, there is some tractable algorithm. Second, there is some, and theoretically, formal proof. The second one is also a formal proof by some version of SGD training. Not super standard, but not super weird at the same time, on a specific network. But in the experiments, we run SGD in a very simple manner. Standard activation, standard initialization, and we show that it works by standard SGD when we run fully connected. Okay. The second one, and the second bullet point, this is a barrier that probably all papers have. They don't know how to analyze the standard dynamics. It's very complicated, so they make some assumptions. They freeze the first layer, then they freeze the second layer, and they update parameters in an alternate way. Okay, so these are the two aspects of each problem we're gonna study. Okay, let's get into the issue of parities with noise. So what is a parity? I have a set S of indices. X is just points are from the Boolean cube, dimension D. Parity just counts how many negative signs, even negative signs I have. And then the parity class is all such functions when I choose the support S. Okay. When X's are drawn from the uniform distribution over the Boolean hypercube, and the label has noise of eta, so with probability 1 minus eta, I'm going to get the right label. Probability eta, I'm going to flip the label. Formally, it's by a Rademacher distribution. Biased Rademacher distribution that gives me 1 probability P and minus 1 probability 1 minus P. Okay, so the label is noisy. The support of the parity is K. It's known that this needs runtime that is exponential in the support size. But intuitively, if we take with probability, some constant probability, we sample from the uniform distribution X, and probability half, we sample each coordinate with a bias somewhere. Then what happens is that we enlarge the correlation of each index so that it's easy to estimate the correlation of each variable with the target label. So what happens is that the average correlation when this index is in the support, let's say it's mu1, and the average of this correlation when the index is not the support, this is the gap in expectation. We can just sample 1 over this number squared, and we can detect with high probability whether high is in the support or not. So I can do it for all indices. I'm going to use union bound, and then I can efficiently recover this support. So yeah, so when I give like some biases, then it's easier to detect. It's easier to detect the support of the parity. This is some intuition. Let's see an experiment.
So this is a D prime that lets you exactly learn the target, and therefore you're able to learn it over any original distribution because you've learned it.
This is exact learning.
So you don't even D prime doesn't even have to depend on D. It's just a D prime that allows you to find the target exactly.
Yeah, in this case.
In this case.
In this case, yeah.
Yeah. Okay.
Okay, so here's an experiment. This is a dense parity. The support is of size 25. Dimension is 50.
Sorry, even in this case, that's true if you learn with gradient descent. Okay, no, but sorry. You can,
This is not a gradient descent.
Yeah, that's an experiment. Sorry, because then you do need actually.
With a special purpose algorithm, you can just pull
Special
out.
purpose algorithm, you know. Yeah.
So this falls under the sum tractable algorithm. Okay, so when I have a dense parity problem, D is 50, the support is of size 25. This is a 2-layer ReLU neural network, standard. And now the way I take the marginal is going to be probability half, I'm going to sample from true marginal. Probability half, I'm going to sample from this Rademacher distribution. What it means, this distribution, it means that each coordinate, I'm going to sample from Rademacher distribution. So with probability 0.98, I'm going to get +1, and otherwise -1. So basically, we're using a mixture with the original distribution and some other distribution that helps me to recover the support. Okay, and this is by 5 minutes. And okay, and this is by SGD. Okay, standard training, and so this red line is eventually, when you don't have positive distribution shift, it's gonna converge after 50 to the 25. So eventually it's going to converge. But here you can see that it converges much faster. Where the baseline is how much noise you have in the distribution. Does it make sense? Okay, so maybe I have 5 minutes. Let me talk about this framework where the training distribution is allowed to depend on the function class I'm learning and the original distribution. So H, function class H is DSPAC learnable by learning rule A. If for any marginal distribution D and any labeling function H from the class, there exists some D prime that depends on D and H, such that for any epsilon, when I sample from D prime, the error with respect to D is going to be at most the noise in distribution plus epsilon. So the statement says that for any D, there exists D prime. It doesn't mean that the algorithm needs to construct this D prime. It means that it exists. And if it exists, maybe we can try to find it. And D prime depends on D and H, not on the target concept, just on the concept class. Okay. And there is a randomized version that D prime of X is sampled for a meta distribution. This is another randomization over the distribution chosen from meta distribution. Okay, so I will show you some results we have for this model, which we call DSPAC. So for parity, there exists some tractable algorithm. I gave you the intuition. When I use GD, we can prove it with some stylized version of gradient descent. We have an experiment. For K junta, functions that are sparse, depends only on K variables. It's DSPAC by some algorithm, deterministic DSPAC, but the polynomial runtime is in 2 to the K dimension. For some variant of GD, we know how to show it that is RDSPAC. It's very likely that this is also the DSPAC, but we don't know how to prove it. There is also compelling experiments. Depth K decision trees are RDSPAC with this runtime. We don't know what happens with gradient descent. DNFs are also RDSPAC with respect to the uniform distribution. We don't know what happens with gradient descent. Yeah. A very recent result, we could show it for a general function class. Function class that is k-sparse in the Fourier domain. What it means that if I take a Boolean function, I write the Fourier representation, then the number of non-zero coefficients in this representation, the number of non-zeros is at most k. So we can show that this is RDSPAC, this is unpublished, and probably also DDSPAC. I think for gradient descent on a neural network, the answer is probably yes, but we're working on that. So this is like general function class that subsumes most of the other results. This is with Nader Bashuti. Yeah, so last point I want to make is that it is connected to the setup of membership queries, but for non-adaptive membership queries. So what is a non-adaptive membership model? Is we have a random sample S from distribution D, and then I can make a batch of queries once that could depend on these samples and to get their labels. But it's like two-phase, like I sample, then I query a batch and I get the results. I cannot adaptively query based on the past. Most work on membership queries allows adaptivity. Don't have time to show this. We showed these connections. Maybe surprisingly, I don't know, maybe it's surprising that many classes are known to be, can be efficiently studied with non-adaptive membership queries, and sometimes the proof are much more complicated. For example, DNFs. I think the proof is very complicated by Vitaly Feldman, a really nice paper. Another also showed recently, a few years ago for decision trees. New result for sparse functions. Effectively, we don't know any interesting class that adaptivity in the membership queries is necessary. We have an example of a syntactic class where there is a separation between adaptive membership queries and non-adaptive membership queries. But for example, for automata, we don't know if it's necessary. Okay, never mind. Let me wrap up. Takeaway, when we study learning dynamics, we should study them in terms of the training distribution, instead of maybe making assumptions on the target distribution. Many open questions. More classes that are DSPAC learnable by GD other than parities and juntas, theory experiments. Natural classes that adaptive queries are necessary as opposed to non-adaptive queries. Crazy conjecture I didn't tell you about, but never mind. Yes, that's it. Thank you.
Questions?
By the way, I think even with this stylized gradient descent, you can exactly learn the period with the same distribution actually. Like it's not only for this like special algorithm.
For this, yeah.
Like if you take the mixture of like uniform and this biased, even like GD can
But the
exactly.
experiment.
I'm not sure with the experiment, but because we use
No,
this
but
like
the-
L1 thing.
You would need the stylized. You would need the huge step size. And only the
Yeah.
stylized in the to be exact. In the experiment, it's not exact.
Maybe one just tiny question. On the slide just before, you mentioned, just so I understand, what, the one before that. Yeah, you mentioned DNF, but then you said, but DNF's membership queries don't help. So what's,
So you can learn DNFs with non-adaptive membership queries efficiently.
over,
Uniform distribution.
it's uniform distribution.
Yes,
Uniform
yes.
distribution.
Uniform.
Uniform distribution with queries.
So with
I see.
adaptive queries, it's
And then-
old result.
Right.
With non-adaptive queries,
That's
it's much more involved.
It's uniform.
Yeah, DNFs is uniform. Otherwise. But the other classes is exact learning. Decision trees, junta, exact learning.
And that was Nader's result about decision trees many, many years ago, learning with queries over arbitrary, like exact learning. That was amazing.
So Nader is actually working on that, on non-adaptive membership queries. And we weren't sure that someone is aware of this model or working on this model, but yeah, it's actually actively working on that. So.
So I think we didn't. What we couldn't find, I'm actually curious, is negative results for non-adaptive membership queries. Because there's negative results for membership queries, but separating between non-adaptive and adaptive membership
And his
queries.
old one was adaptive.
Sorry, what?
Yeah, and his old result was adaptive.
It was adaptive, right. So now we're working with him on non-adaptive. So it's probably possible to do it non-adaptive. That's what we're now working with him.
So sparse functions, we can do it with non-adaptive queries. Maybe DFAs
Well,
is
decision tree is always a special case of sparse functions.
Right.
So I mean that's what Nader showed. So basically, with the Idan's method for sparse functions, you can learn decision trees with non-adaptive membership queries.
it's more general. Yeah.
All right, other questions? All right, thanks.